About the filters problem, we have seen how to calculate omega 3 dB, right? This is very important concepts. We have so many questions related to this one concept in the GATE examination. So today also we'll discuss about the omega 3 dB. We'll see some more problems based on filters. Then we'll switch to the oscillators. Okay friends. So for any system, bandwidth and gain product is constant. Bandwidth and gain product is constant. Okay. Suppose you are considering open loop of op-amp. You are applying V1 over here. You are applying V2 over here. Let's take gain A. You are taking output V0. And you know in the open circuit output is given by directly the gain multiplied with the difference of the input. So that's why we call it the differential gain. Okay friends, so for this system, whatever bandwidth is given, we will multiply that bandwidth with gain, we'll get something. Let's take, we are getting K. Okay. For this system, bandwidth and gain, multiplication of bandwidth and gain are constant. Now, in the second stage, what you are doing, for the same system, we are not changing the system. What you are doing, you are introducing some negative feedback over here.
So here what we are going
and
to do is,
if you introduce negative feedback, the gain and bandwidth both changes. Is it okay? There are so many changes in the system if you will apply the negative feedback, but especially gain and bandwidth both will change. But after applying this feedback, again when you will multiply this gain and bandwidth, you will get constant K always. So what I am saying is, for any system, before and after applying the feedback, the bandwidth and gain product will always remain constant, always same. Is it okay? This is very important concept. Now based on this concept, we have asked one question in the GATE 2015 paper. It was 2 marks problems and very easy. If you are clear with the fundamentals, within 30 seconds you will do the problem. Okay friends. So let me take the circuit
is in the
over
RE.
here.
When RE will increase,
the
AC will decrease. So AC is going to decrease.
Fine.
Do we have any
This
option
is plus,
here? AC is going to increase, option is
AV
there.
over here.
Now AC is
The
decreasing.
non-inverting
What
terminal
about
is connected
CMRR?
with VI.
Definitely by this formula,
Perfectly fine.
CMRR is nothing but
Here we are
AV by
taking
AC.
output.
AC is going to
And this
decrease.
is the negative
CMRR
feedback.
going to
So
increase.
here
So
I'm
correct
taking
answer
negative
is
feedback,
CMRR
but in this
going
way.
to increase.
This is
Okay
nice.
friends. So friends, this is all about the third unit, operational amplifier, in this unit also I joined the feedback amplifier. So in the last unit we have remained with oscillators
one
and power amplifiers.
In series
We'll come
and
soon
over here
and we'll meet
we are
soon over
taking
there.
the negative feedback.
So friends,
this is the
let me
circuit
tell you
given.
one thing.
Now the
Please
question
do
says,
practice at your home.
an op-amp
Okay.
has ideal
So
characteristics.
we'll meet in the next. Till then,
Except
take care
that its
and bye.
open loop gain is given by expression. If you will find out the open loop gain for this circuit, they are mentioned the open loop gain for this circuit, and that is AVS. AVS is given 10 to the power 4 divided by 1 plus 10 to the power minus 3 S. Is it okay friends? This is open loop gain they mentioned. Okay. Now the question says, this op-amp is used in the circuit shown in the figure. Okay, no problem at all. The 3 dB bandwidth of the circuit in radian per second is, the 3 dB bandwidth they are asking for this circuit is. Okay, you have options also. Option A is given 10 to the power 2. Option B is given 10 to the power 3. Option C 10 to the power 4. Option D 10 to the power 6. Okay, and you have to find the band omega 3 dB in radian per second. The unit is also given in the question itself. Okay, again I am telling you, you have given with this op-amp circuit, the open loop transfer function open loop gain of this system is given over here by this expression 10 to the power 4 1 plus 10 to the power minus 3 divided by s. Okay, this is the open loop. Now the question is they're asking for the omega 3 dB. We always calculate omega 3 dB after see, this is the given expression of AVS. Is it okay? Or I can say this is the transfer function when feedback is not there, right? So omega 3 dB we have to calculate after feedback. Today we are going to start the fourth unit, that is oscillation and power amplifier. Okay. Observe, but before going to start that
this
unit,
is the given
we cover some miscellaneous topic
like
which
K,
I couldn't complete yet.
let's take it
We'll complete it first, then we'll switch to the S tau. Okay, friends. Here, this is the expression or transfer function.
Okay.
In the open loop
first
system. Topic of the day is current mirror circuit. Current mirror circuit. Or also the
Whatever
another
gain
is
is
there,
there,
that is
constant
current
current
provider system, because there is no loop there. Okay, I'm sorry. So directly the transfer function is given A divided by 1 plus S tau
source, I can say.
where gain is 10 to the power 4.
So what is the current mirror? Let me
From
draw
this
the circuit
expression
first.
getting the circuit for the current mirror is, you can see over here, perfectly fine. They are common to each other. This is the terminal, collected terminal of the Q2. Two transistors will be connected in this way, and this will be common for both of them. Here the
Gain is 10 to the power 4,
base will
perfectly
be
fine.
connected over here.
And we earlier
Now
find that
what current
what
mirror
is
concept
the
says,
omega 3 dB for the
current
given
mirror
transfer
says,
function.
as the name suggests, the
Omega
current
3
will be
dB
mirror is always 1 by
Q1
tau.
and
Is it
Q2.
okay? Over here the current
Tau
mirror
is
says if
my
the
10 to the
current
power
over
minus
here
3,
is
so
I reference or IC, same current will flow over here also. This is the current mirror concept. Is it okay, friends? So true BJTs are connected in this way
for open loop.
Q1 and
Open
Q2,
loop, okay, is 10 to
and
the
the
power
base
3
is common
radian
for both
per
of
second.
them, or base is connected at
So this is
single
given
point.
for open loop. But we have to find omega 3
collector
dB for
current
this
is equal
circuit.
to the, is it okay? Alright, though we can say the IC1 is equal to IC2 in this case. How is it possible? Let's see it, okay? So current in this,
to the
suppose
power
let's
3 in
take
the options.
IC. Many students are,
Okay, so base current
you
will
know
be what?
tell me,
Giving answer
the
10 to
base
the power 3
current directly by observing this only. So in the examination, they are not asking about the omega 3 dB for the open loop. No, they're asking for this circuit, and this circuit is the closed loop, right? The feedback is given over here. So what we have to do? For the input stage will be definitely IC by
in one
beta,
case
where feedback is not there, the relation between
gain
IC and beta,
and omega 3 dB
IC
both.
is nothing but beta
It means
times
I
of
have
IB.
bandwidth.
So
and
IB
gain
will be
product.
definitely IC by beta.
Is it okay?
If you know the value
What
of
is
IC.
the bandwidth
Okay,
and
correct,
gain
no
product for
problem.
this circuit?
And both
the gain
are
is 10 to
identical.
the power 4.
So this
No
one
problem.
Q2 also fetch the current, that is IC by beta. Is that okay, friends? What it means, in this branch you are getting 2
And
IC by beta.
the
current.
gain
Is
gain
it
is
okay? 10 to the power 4 and the omega 3 dB is 10 to the power 7. So K is, I'm sorry, this is 3. So K is 10 to the power 7. So what I mean is gain bandwidth product should be constant.
Okay.
Means,
Okay, friends.
now if
So
you
this
take this in the
this
negative
current,
feedback,
the base
current is IC by
if your
beta
op
for
amp is working
Q2,
in the
what will be
feedback,
the collector current for this?
then
Definitely it
also
will
your
be
band-
IC. Gain and
it will be
bandwidth
IC
product
or not?
will
Tell
be
me.
10 to the power
You know the
7 only. Now I think you can easily get what they are asking and how we can do it. See, now for this circuit, whatever is given over here, we can calculate gain or not. Tell me. For this given circuit, Can you calculate V naught
Now
by
you can
VI?
multiply the base
current by beta,
so you
will get the collector current.
Let's calculate it.
When you multiply given this circuit quantity with beta, you will get IC. Okay. Now friends, what current mirror circuit is saying? This I reference is the current from this source is equal to this IC. The concept says I reference equal to IC. Is it okay? But I reference, how it become ICC? Here in this case, in this branch the current is going to IC by
Though
this
beta,
is the negative
branch,
feedback, the current is going only
the VI
IC, and
over
I
here,
reference is
the
summation
same
of
is
both
over
of them.
here,
If
VI.
you will apply the nodal analysis
In
at
this
this
branch,
point,
current
you will
is
get I
zero.
reference equal
So
to this
9K
plus
and
this.
1K, both
So
are connected
both
in
current
series.
IC plus
So this
2
V
IC
naught
by
will be
beta
dropped.
will add like this. Is it okay? Now why we across 1K? So what will be the value of voltage across Vk? That is Vi over here given. So what is the value of Vi in terms of V naught? So 1K into V naught, 1K into V naught divide by 9K plus 1K, 9K plus 1K. So this is nothing but, if you'll find out, Vi equal to V naught by 10. So what is V naught by Vi? V naught by Vi is 10. So you have find out the gain. Now they're asking omega 3 dB or the bandwidth. Now what you have to do, the gain multiply with bandwidth is equal to 10 to the power 7. Is it okay? How you got this 10 to the power 7? By input stage. Or you can say it's not input stage, the stage when feedback was not introduced into the system. Okay. So direct expression was given. It means gain and bandwidth product was given. In the second stage, we have to find the omega 3 dB. Gain is given by this circuit. So gain is 10. Omega 3 dB they are asking is equal to 10 to the power 7. So it will cancel out one time and you will get omega 3 dB is equal to 10 to the power 6. Is it okay? This is radian per second. So this is the way of solving this type of problems in which omega 3 dB they are asking. So omega 3 dB is nothing but bandwidth. Okay. This is bandwidth also in radian per second. Is it okay friends? I hope this point is clear to you. Let's come to the next problem. So in alternative years we are asking by this type of questions again and again based on this filter and all. This is again in GATE 2012. For 2 marks we have asked this question. The question is the R1 over here, R2. This is the circuit of an op-amp like this. V0 connected over here. Everything is given. Over here I am applying V in. This is the capacitor. Now the question reads as, the circuit shown is A. Options are given. A equal to LPF and F3 dB is given. F3 dB is given. 1 R1 plus R2 C and given in radian per second. So it's obviously omega 3 dB. Okay. Now the option B is given HPF with the same frequency. No, frequency is changed now, 1 by R1C radian per second. Okay. So 2 times HPF and 2 times LPF they are asking in the option HPF with this frequency, HPF with this frequency. Over here also. Okay. So let's come in. First, identify which type of filter it is. It's low pass filter or high pass filter. Omega equal to 0. This will cut off. Definitely you will get V0 equal to 0. Okay friends. Omega equal to infinity. This will be short circuited and you will get definitely some output in the form of V in. it means it's HPF. The low frequency components are blocked over here. So this is HPF. So the answer will be HPF, but you have two options of HPF. Now, I told you earlier the short trick how to find the omega 3 dB. Omega 3 dB for any circuit is 1 by tau. Is it okay? This is the stage for which we can easily find out what is the tau. Tau is nothing but R1C. Is it okay? So why I'm not considering this R2? Actually, while calculating time constant, you have to see capacitor only, and capacitor and resistor up to ground. So here we have ground. So I'll proceed up to over here only. Okay. So I'll get only resistance R1 in the circuit. So this capacitor into this R1 is nothing but R1C. So your omega 3 dB for this case is 1 by R1C radian per second. So your option is, this is HPF with omega 3 dB equal to 1 by R1C. Is it okay? 3 to 4 times they ask the same time of question with us. Let me consider the next one. Okay. So based on the same formula, again they ask 2 marks question in GATE 2007. Okay. And the question is, if you know direct how to solve it, then you can get the answer. If you don't know, then you have to work hard to get answer for this. Okay. This is 330 PF is given. Perfectly fine. This is the capacitor over here, again 330 PF. This is the input stage given, plus minus negative feedback given, V0 10K is given, everything is given, and this is connected over here. This is your circuit given. Consider the circuit shown below. The correct frequency response of the circuit is. Now he is not asking this is low pass filter, high pass filter, what. He is given directly the output. Okay. So the first one is given. This is like this. 4 dB is given over here. And at 21.9K, this is 1 dB. Okay. And the slope is 20 dB per decade. Okay. And in the next option, the same graph is given. The slope is 40 dB per decade. And this cutoff frequency is 21.9K again. This is minus 3 dB. This is the option. And I'm considering the third option also. In the third option, it's 40 dB again. And this is like this. So 21.9K the cutoff frequency, and this is 1 dB. Okay, friends. Now, we have to solve with this. If you'll, form the equation of all this, it will take 6 to 7 minutes to crack it. And we don't have to give 6 to 7 minutes to only one question. And still, there will be ambiguity that you are right or not, because it will be very typical to solve this. Okay. Because capacitors are involved. And here, how many memory elements are given? See, here 2 capacitors are given. One is this and one is this. 2 capacitors are given. And we can't resolve these 2 capacitors. Mean they will be always present in the circuit in different way. Resolve means they are not connected in series or parallel. If 2 capacitors are connected in series, we can make them 1. If 2 capacitors are connected in parallel, we can make them 1. But these 2 capacitors can't be made 1. Why? Because they are different. They are not in this fashion that they are connected in series or parallel. So how many memory elements are there? 2 elements there, right? So we'll get 2 terms. Means the order of this will be 2 always. Means in denominator, we'll get 2 poles. One because of this, one because of this. Right? So for single pole provide 20 dB per decade, 2 poles will provide 40 dB per decade. So the slope of the line will be definitely 40 dB per decade. In the fourth option also, it's HPF given actually. In these three options, they have given LPF, LPF, LPF. In the fourth one, they have given HPF. So we can easily eliminate the HPF. Why? Because now we'll identify whether it's LPF or HPF. Okay. See, now we'll find its high pass filter, low pass filter. Let's consider omega equal to 0. Omega equal to 0, these two things will be open and definitely will get output. Definitely will get output. But if omega equal to, let's take omega equal to infinity. At omega equal to infinity, this will be grounded. Okay, when this will be grounded, the voltage over here is grounded. And if you drop this V naught over here, you will find that V naught is equal to 0. So definitely it's low pass filter. So now two things you easily identify. Number one is, this is LPF. So out of four options, you have LPF in only one option. Sorry, HPF in only one option. That is the fourth option. I did not consider over here. So in three options we have LPF. So how to eliminate now? Now again we can eliminate two options. Only one option again I can eliminate. See, over here it's given 20 dB per decade. 20 dB per decade is for first order, but this is the second order, right? For the second order, definitely you'll get 40 dB. Now you have remained with two options. And if this is cutoff frequency is same for both the circuits. So cutoff frequency is the frequency where magnitude in linear is k by root 2 or 1 by root 2 of whatever magnitude given. Okay, but in dB it's 3 dB. That's why we call this is the omega 3 dB. Omega 3 dB means the cutoff frequency at gain 3 dB. Or 3 dB is equal to 1 by root 2 of k only. Is it okay? So easily without calculating we can solve this question. But if you want to calculate this 21.9 k, I told you this is 20 k given over here. For any one of this circuitry you can calculate this. Omega 3 dB, omega is nothing but 1 upon RC. Where you have to consider, if you are considering this 2, so you have to take this 2. 22k into 330 picofarad. So if you will solve it, you will find out 21.9 k. Okay friends. Now let's come to the next one. The next question is given. The circuit I am drawing over here. 1 mega capacitor over here, connected directly to V naught. No problem at all. Over here it's 500k grounded. V naught connected, minus, plus. The feedback is coming from here. This is grounded. Okay. Over here you are applying V input. This is 1 microfarad. 1 mega ohm, 0.5 given in microfarad. Okay, both. So this is the question, and the question is very simple. 2 marks question, 2011 gate. The ideal op-amp based the circuit shown below act as a 4 options. Simply LPF, B HPF, C band pass filter, and D band reject filter. The question is very simple. So let's take omega equal to 0. Omega equal to 0, this is turned off. So this circuit is turned off. You are getting V naught. Is it okay? No feedback is there now. So how you will get this? You will get this directly. So in this case, I think it will become without feedback system, because this will be open, this will be open. So circuit Vi is present over here, everything is over here. So definitely we'll get output V0 gain into difference of input V in minus 0, because non-inverting terminal is connected with 0. Okay, so definitely we'll get output over here. So you'll get output in the form of V in. Now if you'll consider omega equal to infinity, then what will happen? Omega equal to infinity, it is short circuit, short circuit, short circuit, short circuit. Now this 0 is over here, this 0 is over here also. So omega 0 equal to 0. So this is low pass filter, clearly shown. This is 2 marks problem, friends, in 2011 only. So see, so many filters questions are given. I have to consider some more and then we'll switch to the next miscellaneous topic only. So this is the question, GATE 20 08, okay? 2008 question. 2 marks. And the question is very simple circuit. Plus, minus, V0, 1 micro, 1K, over here Vi, over here 1K, 1K, connected over here, and like this, okay? Everything is given over here. The op-amp circuit shown below is that of A for options. LPF with a maximum gain of 1. A max is given 1. Option B, again LPF, and gain is 2, maximum gain. C is HPF, and gain is 1. And D is again HPF and gain is 2. Okay, very easy, 2 marks problem, 30 seconds hardly or 1 minute problem if we'll find out the gain, okay? So friends, first find out whether it's LPF or HPF. At omega equal to 0, the Vi is disconnected from the circuit. If Vi is disconnected from the circuit, definitely you will get V0 is 0. Now, omega equal to infinity, Vi will be there. This Vi will come over here. Definitely in this case we'll get something. No problem at all. So definitely it's HPF. So now we have 2 options. Now find out the gain. So to find out the gain, what you will do is, so gain you have to calculate, and gain is the kind of AC analysis. It will be short circuit. Vi will be over here, and its Vi is over here also. So what is the relation over here? The relation is Vi equal to V0 by 2. So V0 by Vi is nothing but 2. So the gain is 2 and it's HPF. Okay friends, is it clear to you? So it's hardly, it will take 30 seconds only. Okay. Now I'll take one more and then I'll come to the offset error. Let me take the circuit. Circuit is a bit complicated over here. Okay, V0, 82, 91, this is also K. Over here you are connected with capacitor, grounded, 22K, 22K, here capacitor, the capacitor value is 0.47 microfarad for both. Over here you have input V in and this is V0, right? So he is asking, this is the latest GATE 2014, GATE 14, 2 marks, and the question is, for the given low pass filter already mentioned, shown in the figure, the cutoff frequency in hertz will be. He's asking the cutoff frequency in hertz. Okay. So we know omega is nothing but 1 by RC. What is R over here? Let's consider only one part. 22K into 0.47 microfarad. Okay. So some people will calculate this and will answer. And some people will find out the proper whatever they are asking. This is 2 pi f of whatever you will get over here. You will divide this K by 2 pi. So you will get your answer. And for this if you will calculate, you will get 15.39 hertz. Okay. So this will be your answer for this circuit. Now we will see the offset error questions. Let's take one more 3 dB related problem. And the problem is given, circuit is given, minus plus, here it's R2 in parallel with C1, V0, it's R1, grounded, sorry, this is VI over here. Now the question says, an active filter is shown in adjoining figure. The DC gain and 3 dB cutoff frequency. The DC gain and 3 dB cutoff frequency. R. Okay. The options are given over here. 400 dB, 3.14 K. It's given in hertz. Option B is given 40 dB, 1 K. Option C is given 20 dB, 6.28 K. All in hertz. Okay. D 20 dB, 1 kilohertz. Okay, the question is, and the values of this R1, R2 and C1 is given. R1 is 15.9 K, R2 is 159 K, and C1 is 1 nanofarad. Okay, question is the DC gain and omega 3 dB. So omega 3 dB, okay, we have to calculate omega 3 dB. Omega 3 dB is nothing but 1 by RC. 1 by RC, what is R and C? They are connected. With the capacitor R2 is connected, we'll consider R2 only. So 1 divided by R2 is 159 K into 1 nanofarad. Okay. So here I have to find in hertz only. So the 2 pi will come to this side. 159 K into 1 nanofarad. So 10 to the power 9 over here. If you will solve this, you will get, it will be 1 kilohertz. So 1 kilohertz we are getting in two options. Okay, this is 20 and this is 40 dB. So what they are asking, second, the DC gain. DC gain means the gain of the system at omega equal to 0. Omega equal to 0, the C1 will not be there in the circuit. If C1 is not in the circuit or the question become very simple. So let me find out. I hope you are getting concept. These are very important. That's why I'm covering this all. Okay. This is 20 dB. Okay, perfectly fine. So calculate, where is the, okay, over here, right? It's 0. So 0 minus V in divided by R1 plus 0 minus V0 divided by R2 equal to 0. Okay. So this V in by R in equal to plus V0 by R2. So V0 by V in will be R2 by R1. R2 by R1. So this is R2 and this is R1. So this will be 10. It will come 10. So your gain is 10. But they are asking in dB. So if you want to convert it into dB, you have to take 20 log 10. Okay, and 20 log 10 is 1. It is 20 dB. 20 dB. So the correct answer is this one. Okay friends, I hope this is clear to you. Now come to the offset error type of questions. We'll see the offset now, right? Let me introduce something. Minus, plus, V0. Over here, the RF feedback register. Input stage connected with R1. It's grounded. Last time also we discussed that the input offset voltage is always given with non-terminal. Okay, it will be always present on this terminal. Okay, so because of this VIO, if you will calculate V0, so V0 will come. See, this is the non-inverting. Yes, this is a non-inverting feedback or non-inverting. At non-inverting terminal, if you will apply the input, so the gain, if you will calculate it, it will come 1 plus RF by R1 of VIO. This is the input offset voltage, and due to this, the output voltage will be this. Okay, this is kind of error. So output due to input offset voltage is given like this. Is there any problem? In the question, if they don't mention this VIO presented over this non-terminal, non-inverting terminal, so you have to take it by default or you have to consider over here only. Okay. Now, let's come to the input offset current, right? For the current, let me draw the circuit. This is R1 over here. It is also grounded. Feedback resistor RF over here. So this is the positive terminal, non-inverting terminal. The current in this is IB plus. Here it will be IB minus. No problem at all. Okay. Now these are the biasing currents. Okay. If you will consider the IB plus and IB minus, these are the biased current. Okay. So suppose you will calculate, you have two currents at input stage current in two terminals, negative terminal and positive terminal. So because of this also you can calculate V0. So I'll call it V0 plus. V0 plus when IB is not there in the circuit, only IB plus is there. Okay. So because of this, if you will calculate, it will be again, everything is there on non-inverting terminal. It will be RF by R1 multiply with the voltage, and voltage drop will be IB plus RC. Am I right? IB plus into RC. This will be voltage over there. Okay friends. Now let's come over here because of minus current now we'll take. Because of this we'll take. If you'll find because of this, you'll get R1 into minus RF by R1. Because of this IB minus, you will get V0 minus. Because of IB plus, you will get V0 plus. But your voltage output because of IIO input offset current is RF into IIO, where IIO input offset current is the difference between IB plus and IB minus. So if you take difference of these two terms, you will get RF IIO. Is it okay friends? So IIO is the input offset current, and IB plus and IB minus, these are the differential current, input biased current. Okay. Or see, three things we have seen over here. IIO, this is input offset current. Input offset current. Okay, we have seen IB plus and IB minus. These are the terminal currents. And one is given IB. input bias current. Input bias current. Okay. So input bias current, this input bias current is the average of these two terminal currents, IB plus, IB minus average. This is bias current, IB. But if we talk about the IIO, so IIO is the differential current, means IB plus minus IB minus. I hope it's clear to you. Okay. So now we are getting output because of two things. Input offset current, due to offset current we are getting, as well as offset voltage also, right? Because of this also we are getting currents. Because of in offset current, you are getting V0 is equal to IIO into RF, feedback resistor. And because of offset voltage, you are getting V0 equal to 1 plus RF by R1 into VIO. This indicates that VIO applied on the non-inverting terminal only. Okay friends. So if we will take the entire V0 because of these two, so it will be the mode of offset output due to input offset voltage plus offset output due to IIO. Is it okay friends? So these are all formulas related to input offset current and voltage. Now we'll see some problems. Okay. This is GATE 2014. 1 mark problem and hardly 10-second problem. And the problem is given. They have drawn the simple circuit. Just show the input, or I can say terminal bias currents. This is IB1 over here, and in this case it's IB2. This is IB1 given over here. Now the question is, for the op-amp shown in figure, the bias currents are IB1. Bias currents are IB1. Yes, IB1 is given 450 nanoampere, and IB2 is given 350 nanoampere. Perfectly fine. Now they are asking the value of input bias current. These two are the terminal bias current. Now input bias current. Input bias current IB and input offset current. Input offset current, that is IIO, they are asking. Okay. So what will be the IB? IB is nothing but we have just seen IB1, IB2 divided by 2, average of these two. What is the average of these two? 450 plus 350 divided by 2. So it will be 400 nanoampere. Okay, and you have given with 4 options also. 800 nanoampere and 50 nanoampere, I'm sorry. 2 is given 800 nano and the second one is given 100 nano. The C1 is given 400 and 50. The D1 is given 400 and 100. Okay. Now, the first one is 400 we are getting. So we are having 2 options only. Let's check the second one. The second one is input offset current. So just we have to subtract IB1, IB2. IB1 is 450 minus 350. So it's 100 nano. So option D is correct. See, this is the very simple, right? Let me take the next one. The question is given. This is 2 marks problem. The question, first the circuit is given. A very simple circuit. V0 100K like this. Over here 100K. it's connected right this VS, and over here this is grounded. Okay, so options are also given. 1 millivolt, option B is given 2 milli, option C is given 2.5 milli, and option D is given 3 milli. Okay, now in the circuit shown in the following figure, the op-amp has input bias current IB less than 10 nanoampere. Input offset voltage is given less than 1 milliampere. The maximum DC error in the output voltage is DC error max at the output. So output offset, these offsets are nothing but the errors, right? We earlier discussed about the total entire we know due to input offset current and input voltage offset is given by 1 plus RF by R1 of VIO plus RF of IIO. In this case, the non-inverting terminal is grounded. In this case, IIO is equal to IB. Both are same. Okay. So we can consider bias current over here. 1 plus RF by R1. So it will be 1 plus 100K by 100K into VIO is given 1 milli plus RF is given 100K into IB is given 10 nano. Is it okay? So this will be 2 milli plus this will be 1 milli. So total you have 3 milli. So your option should be 3 milli. Is it okay? This is the maximum DC error we can have. We choose the maximum value, so obviously we'll get the maximum DC error. So as we discussed, the offset is nothing but the error. Is it okay? Undesirable input. VIO and IIO both are undesirable. What is desirable? See, IIO is given by IB plus minus IB minus. Is it okay? So we are getting this difference. But ideally, in the ideal op-amp, the current is 0 over there. And if current will flow into these two branches, the current should be same. The current should be same. The virtual ground concept will make this voltage and this voltage equal. So current should be same. Current should be same. IIO will be 0. So ideally, the input offset current should be 0. Is it okay, friends? So this is unnecessarily undesirable current. Because of that, we are getting output. Output is RF IIO. Okay. And because of input offset voltage, undesirable output is 1 plus RF by R1 divided by VIO. Is it okay? Now we'll take one last question from the filter and we'll wind up this session. Okay. The question is given RC minus plus. Here I'm taking V0. Over here connected with L and R. This is L. Perfectly fine. V input. Okay. The options are also given. Pi by 2. Pi. 3 pi by 2. And D is 2 pi. So what is the question? The question is, the op-amp shown in the figure below is ideal and R equal to under root L by C. The phase angle between V0 and VI. They are asking the phase angle between V0 and VI. Or the difference, the phase difference of this they are asking. Okay, friends. So, at what point we have to calculate omega equal to 1 by root LC given. So again I am repeating the question. The question is, this is the circuit. We have to find out the phase angle between V0 and Vi, if these are the condition, and this particular thing we have to find at omega equal to 1 by under root LC, where R is given this. This is C over here, this is R over here. Okay friends, I have to calculate the phase difference. So let's find the transfer function. Let's find the V0 by Vi. Okay. I have to replace these two things. Now I can erase this. I'll take the equivalent of this two capacitor and this inductor L. This is R over here. This will become Ls and this will become 1 by Cs. Now this becomes 0 because of the virtual ground concept. Here at the point A, I'll apply the nodal analysis at point A. So 0 minus Vi divided by R plus 1 by Cs. So 0 minus V0 divided by R plus Ls equal to 0. Okay. So let's take V0 to this side. So it will become plus V0 and this. Now V0 and Vi, the transfer function will be V0 by Vi equal to R plus Ls divided by, this will be minus. Let's take minus over here. R plus 1 by Cs. This is given over here. Okay friends. Now the conditions are also given that R equal to under root L by C, and I have to find the phase difference of this entire thing at omega equal to given 1 by under root LC. Okay. So if you will replace this S by J omega, this is R plus L J omega. No problem at all. If you find this in denominator, it will be R plus 1 by C J omega. Okay. When you will take G upside, now let me erase this part. Okay. Everything is gone. So your transfer function you have find out is R plus L omega J divided by R plus 1 by C J omega. Multiply with J in numerator and denominator, so it will become minus. And you can remove J omega from here. So you are remain with R plus L omega J divided by R minus J by C omega. Okay, now they are asking find out the, this is V0 by V in. So we have to find out the phase angle between these two. Okay, so simply take the phase of this, and how you will do that? Here the R is given in the question, and R is given root L by C. Just replace it. Root L by C over here plus L. We have to find the phase at omega equal to 1 by root LC. So this is 1 by root LC J over here. Here it is again L by C like this minus J. This is C and root LC will come up. Let me clear some parts over here. Okay, are you getting? So now we'll get the difference. Okay, the phase angle difference. Wait a minute. So what are the equations we are getting over here? The equations we are getting, this is the transfer function and this divided by this we are getting, right? So in the numerator L by C plus J times of, here also you have L by C. Okay, perfectly fine. here it will be like this, L by C, L by C. Again, over here L by C, you can take common, 1 minus J inside. From here also you can take root LC, 1 by under root L by C is cancel out this, so you are remain with 1 plus J, 1 minus J. Okay friends, so 1 plus J, the angle is, so angle provided by this is 45, means tan inverse 1 by 1 is 45, and for this it's minus 45. If this will go up, it will become angle 90, but before angle 90 I have negative sign also. If you remember, in the starting V0 by Vi were negative, so this negative sign come over here. Minus 90 means, is there minus 90 given? No, not given. So which one is the, wait a minute, over here let me show you. You are getting minus 90, means over here you are minus pi by 2 you are getting, but you don't have any option, so you have to come with positive sign only. So you have to start your journey from positive direction. You are getting pi by 2, you are getting pi, you are getting 3 pi by 2. So your correct answer is 3 pi by 2. Is it okay friends? So this is all about this all. We have covered each and everything friends. We have covered so many questions over here. I think your concepts are pretty clear now. Okay. In the next video onwards, we'll start our oscillation and power amplifiers. Okay. We'll meet in the next. Till then, take care and bye.